All right, what is up, everybody? 2021 AP Stats free response. Let's go. Number one, calculator at the ready. NumWorks, of course. Number one, the length of a stay in a hospital after receiving a particular treatment is of interest to the patient, the hospital, and insurance providers, obviously. Of particular interest are unusual short or long lengths of stay. A random sample of 50 patients who received treatment, the treatment was selected, and the length of stay and number of days was recorded. All right, so we got length of stay and we got number of patients. So let's see, we got the outliers to the right. Oh, so they show it in a table and they show it in a dot plot. Fantastic. Determine the 5 number summary. All right, so 5 number summary means we got to split it into quartiles, into quarters. So let's first think about how we got 50. So we're going to have like 25 and 25. So let's find the median first. So we've got to look at number of patients and count up to 25. So there we've got 17. So the 25th, because what's 17 plus 14? 31. So the 25th is going to be 7. So the median is 7. And then we have to look at the lower half and say on the lower half we have 25. So the 13th is going to be the median of the lower half. And that's going to be Q2, the second number of the summary. Or Q1. Q1, I suppose. Q2 is the median. Q1 is what we're looking for now, the 13th. So here is 4, which means the 13th is going to be here in 6. So the median of the lower half is 6. And then we got to look for 13 on the upper half. So we go 1, 2, 8. So the 13th is going to be in the 8. So the 5 number summary, and then it's the min and the max. So the minimum is 5. But then the max is 21. And so that might be an outlier. We'll probably be asked to do calculations about that. But that is the 5 number summary. And I don't think we have to really label anything. Maybe we will, just in case. We got the min, we got the max, we got the median, we got Q1, and we got Q2, or Q3. Sometimes I've been known to call that Q2 and call this Q5, or Q4, actually. Because in the first one, as it should be, could be called Q0. But yeah, min, Q1, median, Q3, max. That's our 5 number summary. And that's all about the median. So you find the median of all of it, median of lower half, median of upper half. Beautiful stuff. Okay. B. Consider the 2 rules for identifying outliers. Method A and method B. Ooh, I kind of thought there was just one. Let method A represent 1.5, got it, and let B represent, oh, okay, 2 standard deviations rule. Using method A, determine any data points that are outliers in the distribution. Right, so method A is 1.5 times IQR. So first we have to find IQR, interquartile range, which if you know what that abbreviation is, it's exactly what it sounds like. The range of the interquartile, 6 to 8. So it's equal to 2. So 1.5 times IQR is equal to 3. So then we have to go to each Q1 and Q3 and say like 6 minus 1.5 times IQR is 3. So anything less than 3 would be an outlier. So there's no lower outliers. But then the same thing over here, plus 3 is 11. Anything higher than 11 is an outlier, which means 21. So using determine, so let's write what we did here. So we'll say 6 minus 3 is 3. No low outliers. And then 8 plus 3 is 11. Therefore, 21 is outlier. And that should be good. That should be good. And then the next part, the mean length of the stay for a sample of 7 is 7.42 days with a standard deviation of 2.37. Very glad they gave that to us. Using method B, determine any data points that are potential outliers. Okay, so here they told us, luckily, that it's 2 standard deviations. I kind of forgot about that idea. So we want to do 7.42 plus or minus 2 times the standard deviation. And we have calculators. So we go calculation. We go 7.42 plus 2 times 2.37. 7. Make sure we typed it right. Yes. So anything outliers are bigger than 12.16 and smaller than 2.68. Very similar numbers. Very similar numbers. Determining data points that are just potential outliers. I think this is good. 21 is bigger than 12.16. Therefore, outlier. And then no lower outliers. Which makes sense. We got a right skewed distribution. Explain why method A might identify more data points. Wait, are there more data points? Wait. Oh, I totally missed the number 11. Shoot. Thank you, AP Stats, for... Wait, that's not the number 11 I'm talking about missing. I missed the 12 right here. Thank you. Okay. Therefore, 21 is an outlier. And 12 is an outlier. Almost missed that. Explain why method A might identify more data points as outliers than method B for a distribution that is strongly skewed to the right. That's a good question. So I would say if it's skewed to the right, you know the mean is going to be further to the right. So I'm going to say method A is based on the median. Which is further to the left. If it is skewed right. So, in method A, the high data points are further from the center you are using. Further from the center that is used compared to method B. Man, I've never really thought of that idea before. I never even used the second idea for standard deviation. So method A is based on the median, which is further to the left if it is skewed right. So in further to the left than the mean if it is skewed right. So in method A, the high data points are further from the center that is used compared to method B. That's as good as we can get. That's yeah, that makes sense. Oh, that's it? Wow, okay. So it was just all about outliers. All right, question 1, 10 minutes. We got 5 questions, and it's supposed to be an hour and 5 for each. So that's 13 minutes each. Okay, we're looking good. We're looking good then. All right, 2. Researchers will conduct a year-long investigation of walking and cholesterol levels in adults. They will select a random sample of 100 adults from the target population to participate as subjects in the study. One aspect of the study is to record the number of miles each subject walks per day. The researchers are deciding whether to have subjects wear an activity tracker to record the data, or have subjects keep a daily journal of the miles they walk each day. Describe what bias could be introduced by keeping a daily journal. Right. So they could lie. If they are trusted to self-report. That's really all you would need to write. If they are trusted to self-report. You could also maybe say, that's all I'm going to write, but you could also say that, like, if they're actually going through the process of writing it down, they might want to walk more to like feel that goodness of writing it down. But I don't think we really need to say that. That's all you have to. They could lie if they're trusted to self-report. So much space for that. That's all you need to say. Was that all the question was asking? Or what bias? Do I need to give it a name? They could lie if they're trusted to self-report. I probably don't need to name it. What is the name? It's not voluntary bias. It's self-report bias. I don't know the name, so I'm not going to try to give it a name. Anyway, during the course of the study, the subjects will have their cholesterol levels measured each month by a doctor. The researchers will perform a significance test at the end of the study to determine whether the average cholesterol levels for subjects who walk fewer miles each day is greater than those who walk more miles each day. Yeah. Selecting a random sample creates a reasonable representative sample of the target population. Explain the benefits of using a representative sample from the population. Selecting a random sample creates a reasonable representative sample of the target population. So why do you have to use a representative sample? Just in a study in general? You need to make sure or just like it'll have, try to explain it like in context. Walking will affect different people's cholesterol differently. So you got to make sure you get like everyone. Walking will affect different people's cholesterol differently. So should I say, is there like differences between groups? Should I specify on that? Walking will affect different people's cholesterol differently. Specifically, there might be groups of people that it has very little effect. So they need to be represented in the sample. I don't really like that answer, but I don't really like the question either. So I think we're going to leave it there and make sure we come back and check that answer. Oh yeah, we didn't even check our answer for number 1. Hold on. We'll do that after this part. Suppose the researchers conduct the test and find a significant result. Would it be valid to claim that increased walking causes a decrease in average cholesterol levels for adults in the target population? Well, it's just not that it causes it, right? Well, they were randomly assigned. Would it be valid to claim that an increased walking causes a decrease? I mean, I feel like the answer is no. Increased walking causes a decrease in average cholesterol level. Should I just specify the fact that like it's not for everybody? I feel like that's what it's. I feel like there just needs to be one like wishy-washy word in there that makes this appropriate, that it's just missing. Would it be valid to claim that increased walking causes a decrease in average cholesterol levels for adults in the target population? Maybe it's just yes. I mean, I feel like they did pretty good. Oh, no, there wasn't random assignment. Oh, yeah, there wasn't random assignment. That's why. So they selected a random sample, but there wasn't random assignment. That's why. That's a very specific thing we can say. There wasn't random assignment of what they did. I mean, that's pretty much it. Yeah, I don't like these types of questions that are just weird. I didn't like really any of these questions. But here, no, there wasn't random assignment. That's really all we had to look for here. I don't think I really need to explain that anymore. So we're looking real good on time. This will slow us down, but let's check our answers. So number 1, A, 5-number summary, 5, 6, 7, 8, 21. Yes. We got points for essentially correct if the response provides correct values for all 5 statistics with labels. Wow. So we did have to label it. We did have to label it. What if you don't label anything? If the response includes exactly 5 unlabeled numbers expressed together as a vertical or horizontal list, interpret the numbers as being the minimum lower quartile. Oh, so you actually didn't have to label them. Okay. You didn't have to label them if they were in proper order. You could put them in an ordered list. So if you just did it randomly throughout, you would get a P. But if you put it clearly in a list without labels, it was fine. All right, good. So here, correctly identifies the 2 outliers in Part B as the patients who stayed 12 days and 21 days. Provides a justification by calculating the lower and upper outlier criteria using method A. It's 3 and 11. Correctly identifies the 1 outlier in Part B as the patient who stayed. Oh, wait. This is. Oh, okay. And then number 3 is for the next part, is 21. Provides justification by doing that. Yeah. I mean, I definitely did all of that. And then here, this was C. Okay. Indicates that the mean is pulled more towards the extreme values in the longer right tail for a strongly right skewed than the quartile. I did that. Or indicates that the ratio of the standard deviation to the IQR. Ooh, that's weird. Provides an explanation that links effects of the skewness to an increased ability of method A to detect outliers relative to method B. Was a greater effect on decrease and to detect the larger increase in standard. That's the IQR one. I think I did that. I definitely think I did that. Let's read what they did. Quartiles and the IQR are less sensitive to extreme values and strong skewed distributions of the mean and standard deviation relative to the quartiles. The mean is pulled more towards the extreme values on the longer tail of a strongly skewed distribution. For a distribution that is strongly skewed to the right, the sample mean will be pulled more to the right towards the extreme values and the longer right tail. As a result, this pulls the value of the outlier criterion for method B. Yeah, so I said based on the center. But yeah, I definitely said that right. Okay. Now, number 2, I was risky with this. Look how long there was. What did I need, though? Indicates that keeping a daily journal could result in bias that would be avoided by using activity trackers and provides a reasonable explanation. I said they could lie if they self-report. Provides a description of bias that refers to at least one of the following. The use of the daily journal may result in a systematic consistent underreporting or systematic consistent overreporting. Oh, so I needed to say that specifically. And something about a biased estimation. So I needed to say they could lie if they are trusted to self-report. They will over-report and skew the mean to be higher. I feel like that got it then. So I really got it all. They could lie if they're trusted to self-report. Indicates that keeping a journal could result in bias that could be avoided. And provides a reasonable explanation. I think I did that. They just said so much. Keeping daily journals could introduce response bias. A response bias due to self-reporting by subjects who may have a poor or incomplete memory of the amount of walking time was done. If most subjects who keep daily journals underreport the number of miles walked because they cannot remember, the estimated mean of the day would be lower. Okay. B, essentially correct, provides an explanation that the use of a representative sample is necessary in order to make a valid generalization. Okay. Refers to the estimation or inference for cholesterol levels in the target population, or an association between cholesterol levels and amount of walking in the target population. I don't understand that. It is necessary to have a representative sample of subjects from the population in order to make an unbiased inference about the differences between the mean cholesterol of adult members of the target population who walk fewer per day and the mean cholesterol levels for all adult members of the target population. They just restated the question. So why do you need it? To make an unbiased inference about the difference between the mean cholesterol level of adult members of the target population? Yeah, they just restated the question. That's disgusting. Ew. Okay. Part C. No, since the treatments were not randomly assigned. There you go. Indicates that the causal inference cannot be made. Provides a valid explanation that is based on one of the following. The lack of random assignment, being an observational study and not experimental, which is the same thing. The existence of a possible confounding variable that is associated. Yeah, like just being healthy already. Okay. Yeah. We might have not got all the points for that one part, but we definitely got all the points for the other part. Other parts. Okay. 3. To increase morale among employees, a company began a program in which one employee is randomly selected each week to receive a gift card. I don't think that would help the morale of employees at all, actually. Each of the company's 200 employees is equally likely to be selected each week, and the same employee can be selected more than once. Ooh, binomial distribution. Each week's selection is independent from every other week. Consider the probability that a particular employee receives at least one gift card in a 52-week year. Consider the probability that one particular probability... Okay, define the random variable of interest and state how the random variable is distributed. Ugh. Well, that's geometric, actually, then, because we have a fixed number of things, and we're talking about number of successes. It's like a geometric CDF type of thing. So define the random variable of interest. X equals number of gift cards received by one employee in a 52-week year. Yes. State how it's distributed. It's geometric. Because what do you need? You need bits. You need binary. Got or didn't get. They're either getting it or they didn't, so it's binary. It's independent because it says so. And then it's a fixed number of trials. That's what the T stands for, is trials. So that's N equals 52. We're doing 52 trials. And then it's like a success and failure, which I never really understood that. But it's the same success rate, which to me was always the same as independent. But it's there. So, therefore, it's geometric. Do little check marks. That should be good. Determine the probability that a particular employee receives a gift card. Okay. So, there are formulas, but you really just do it, right? So you go, there's 200 employees, so the probability of getting the gift card is 1 out of 200. Receives at least one gift card. Actually, no, maybe we will go to the formulas. Isn't the formula sheet just up here? Because then all we have to do, we don't even have to think about it. We just go to geometric distribution. Oh, but we're not looking for the mean or anything. We're looking for the probability. So maybe we don't just think about those. Just think about the situation. So what is the situation here? He wants to receive at least one gift card. Oh, right. So you do 1 minus the probability of receiving 0 gift cards, because you're either going to get at least 1 gift card or 0 gift cards. So we're going to find the probability of getting 0 gift cards, which means this 199 out of 200 probability that you lose, you hit that 52 times in a row. So 1 over 99 over 200 to the 52. That's the probability of never winning, which is probably going to be pretty low, actually. The probability of losing once is pretty good, but the probability of losing 52 times in a row is, well, still pretty high, actually, unfortunately. So about 1.77. So then we're doing 1 minus that answer. So determine the probability, 0.229. I know on calc you need to do 3 decimal places. I really thought on stats it was just 2, but it's kind of weird that it's different. But that's definitely it. There's a 23 roughly % chance that a employee will receive at least 1 gift card in the 52-week year. And that makes sense, because you think roughly a quarter, right? There's 52 weeks, there's 200 employees, so there's roughly a quarter chance that you're going to get one. B, calculate and interpret the expected value for the number of gift cards a particular employee will receive. That we just go to the formulas. So we do, it's a simple one, I think I just remember it. It's 1 over the probability. Wait, there's no n involved? Wait. I'm saying this all wrong. I'm sorry. I'm totally misguiding you. This is not geometric. Geometric is... This is not geometric. This is binomial. Binomial is a fixed number of trials. Oh my gosh. No. Stop. Binomial is a fixed number of trials. I haven't submitted my answer yet, though, so it's fine. So this is binomial, and this is really supposed to be in with fixed number of trials. Bits, I don't know, bits was until success. I don't know where I was on that. But yeah, binomial is bins. You got still the binary, independent, success, and failure. That's the same for both of them. If it's a fixed number of trials, it's binomial. This is a binomial distribution. And so I realized that when I came up here to find the expected value, and there's no n in the geometric formula, because that's not what geometric is. Geometric is how many do you need until you get a success. So you could say on average how many weeks until the employee gets a gift card. That would be 1 over 200. So very clearly 200 is the expected value. You'd expect to get 200 weeks until you get a gift card. But that's not what they're asking here. They're asking how many gift cards do you expect each employee to get. And so that's that n times the probability of success. Oh, right. N times the probability of success. That was wrong. So we're going to do... Okay. You're getting slappy here. This is the first time that I'm seeing these questions, though. So the expected value for gift cards of a particular employee will receive in a 52-week year. So we're doing n, which is 52, times the probability of winning a gift card, which is 1 over 200. So the answer is 52 divided by 200. That is 0.26. I did not need a calculator for that. So on 0.26 gift cards. So the average employee will receive 0.26 gift cards per year. And that's really just all they want, I think. I don't think they want me to say something about, like, which that also means roughly a quarter of the employees will earn a gift card. Well, that's not true though, because some will earn it multiple times. The average employee will receive 0.26 gift cards per year. Yeah, that's all. That's all you'd want to say for that. That is all you would want to say for that. Okay, next. Suppose that Agatha, an employee at the company, never receives the gift card for an entire 52-week year. Well, that's probably rigged. Agatha deserves one. Based on her experiences, Agatha have a strong argument this selection process was not truly random. Okay, no, never mind. I take that back. It was not rigged. No. No. I mean, I could calculate the probability. Well, yeah, the probability. I already calculated the probability. The probability that she receives at least one gift card in a 52-week year is only 23%. No. There was only a 22.9% chance that she would get one. It makes me feel like I got my number wrong there. But no, they're giving out one gift card out of 200 employees. Yeah, no. There's only a 22.9%. Yeah, no. Agatha's just being ridiculous. All right. Let's check the answers. Question 3. Defines the random variable as the number of gift cards that a particular employee receives in a 52-week year. The number of gift cards received by one employee in a 52-week year. Yes. Describes the distribution as binomial. With a p of... Oh. I didn't say that. State how it's distributed. I didn't state those. I did state that n is 52. I didn't do the probability of success. I did it later. I used that, but... Identifies the event of interest. Identify the correct boundary and direction of the event. Whoa, 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 whoa. I didn't talk about this at all. Provide supporting work to identify the correct probability. Oh, wait. That's the other side. That's part 2. Okay. Oh, so that all goes together. Okay. So I should be safe. They used one extra decimal place than I did. So, I definitely did that. Yeah, I definitely think I just did all of that. Yeah. So it just wasn't in like the parts that they wanted necessarily. Or I don't know. Maybe I didn't get points for showing the P. I don't know. That's close. I suppose I should have wrote... That is specific, because that does define the distribution, right? That the n is the 52, and the probability of success is 0.005, or 1 out of 200, is what I actually would have written. All right, I suppose we can put that next time. But we really did get everything for the next parts, and we satisfied everything in the first part, like in the next part, I feel like. So B correctly calculates the expected value of 0.26, we see that, and provides supporting work for the calculation of the expected value, which is just the 52 times 100, same thing they did here. Provides a reasonable interpretation that includes at least 2 of the following aspects. The concept of repeating the selection process over a long period of time. Oh, I did not do that. The concept of an average or mean. I said average. The context of receiving gift cards. Well, I only needed 2. The random process selecting one employee each week to receive a gift card is repeated for a large number of years that each employee can expect to receive. Yeah, so I only needed 2 of them. All right, cool. C. No, Agatha's experience does not constitute strong evidence. In fact, it is quite likely. Yeah, indicates Agatha does not have a strong argument, provides a relevant probability or expected value, provides an explanation that correctly links the probability. I feel like I did that. Examples that satisfy component 2. The probability that Agatha will receive at least one gift card in a 52-week period. Yeah. So I satisfy component 2. And that's definitely satisfied component 1. Did I satisfy component 3? Provides an explanation that correctly links the probability to the decision. I feel like I did that by saying only. I don't know. Maybe I didn't do that final bit. But that's okay. I got the bulk of it. All right, number 4. Don't look at the answers. A manager of a large company that sells pet supplies online. Ryan Cohen. Wants to increase sales by encouraging repeat purchases. The manager believes that if past customers are offered $10 off their next purchase, more than 40% of them will place an order. That's a strong belief. To investigate the belief, 90 customers who placed an order in the past year are selected at random. Each of the selected customers is sent an email with a coupon of $10 off the next purchase if the order is placed within 30 days. Of those who receive the coupons, 38 place an order. Wow. Is this convincing statistical evidence at the significance level? Wow. They're asking a lot of us here. Okay. So, we've got to do a P test. We got to do a 1 sample Z test for proportions. So we have to show 1 random, yes, 2 independent, I mean, so it should be less than 10% probably. Probably more than 900 customers. Or I should say 90 times 10. Or should I say 90 is less than... what should I say here? Probably more than 900 customers. That's fine. I'll just leave it at that. And then 3 is 10 success, 10 failures. So, but it's supposed to be based off of the probability you assume, right? 40%. So, this is the normal condition. So you do 0.4 times 90 is greater than 10, and 0.6 times 90 is greater than 10. Because you're supposed to use the values you assume, not the actual experimental values. Because the whole idea of of this test is that you're assuming the 40% is true, and then you're calculating the probability of getting the result you got if the 40% is true. So we meet all of these conditions. So we'll do the test. So what is the test? Well, I need to think about it for a second. Well, we have to state our things, right? We have to, I don't even remember everything you're supposed to do. We're supposed to state the null hypothesis. We're supposed to state that our null hypothesis is that the mean is 0.4. Or should I say P is 0.4, since we're not dealing with means. P is 0.4. The alternative hypothesis is really just that it's not, right? What do they want to investigate? Manager sells sample size, wants to increase repeat purchase. Manager believes that past customers more than 40%. To investigate the belief, 90% of customers will place an order. Wait, what does he believe? Believe that if past customers are offered more than 40%. So he believes more than 40%. But your null hypothesis is always an equal. I still think, yeah. Or I guess no, the alternative hypothesis would be that it's greater than 0.4. He just already believes that. That's why I think it's weird. So, but he already believes that, but it's not necessarily true. So that is what he's trying to show. That's what there would be news. There would be news, and he would care if it was greater than 0.4. Yes. Okay. What else do we have to do? I don't remember. I mean, I can do the calculation. So what is the calculation? We go... It's using 5%, so that means our Z star is 1.96. And he just wants to think that it's greater, so let's draw it out. So we're going to have our mean of 0.4. We have to calculate the standard deviation or the standard error, whatever you want to call it. And it's, again, it's based off of the assumed results, because we're assuming these are true. That's why we're drawing our mean at 0.4. And so this is going to be 0.4 times 0.6 over the sample size of 90. That's just a formula. So that's the square root, 0.4 times 0.6 over 90. It's about 0.0516. So then you've got to look at the standard deviations above and the standard deviations below. Or not below, I guess. We're just looking above. So what is this? This 2 standard deviations above. So answer times 2 plus 0.4. It's about 0.5. 0.503. So if we're anything bigger than 0.503, then we've got good results. So what are we actually at? Well, we were at... So we thought 40% of them would place in order. He got 38 of them, wasn't it? That's not very many. 38 of them? Yeah, ew. Out of 90. Wait. Okay, no. Okay, that's good. That's good. I thought that'd be less than 40. No, the actual results are then right here. See? 0.42. That's actually not how you do a significance test, though, is it? How you do a significance test is you calculate a p-value. Oh, shoot. That's more of like a confidence interval, I guess. How do you do a significance test? You find that 0.42. You subtract it. So you find that 0.42. You find our actual probability. You subtract it from that. So then you get the difference. And then you divide that by the standard deviation. So that's the z-score. So then we go, it's like standard deviation. Oh, we go p minus p hat over the standard deviation is 0.43. And then you have to go... Or that's not even what you have to do. You don't even have to do all that calculation because you have calculators. You go distributions. We're already in normal. And we want to look at the probability between... Or no, we don't. Because we're looking at a tail. We want to look at what is the probability of getting 0.42 or higher. Oh my gosh. Okay, hang on. Back, because we got to change our parameters. So the mean is 0.4. The standard deviation is 0.0516. And then we make sure we're going on the right side. We say, what is the probability of getting anything from 0.42 or anything greater than 0.42? And then we look and we see that it makes sense. And so we say, what is the area of this probability here? It is 0.349. That's the p-value, right? Well, we've used multiple different p's now. That's a lowercase p. And then we'll say, because the p-value is greater than 0.05. Let me change colors so I can differentiate this. Because the p-value is greater than 0.05, we reject the null hypothesis. There is evidence to indicate there is not evidence. Wait. No, since the p-value is greater than 0.05, we fail to reject the null hypothesis. What am I talking about? We fail to reject the null hypothesis. No. Because that's very likely. It's saying if the actual answer was 0.4, the probability that we got that result is like 34%. That's very likely. 1 out of 3 times we're going to get a result like that if the actual value is 0.4. So there is no evidence to show that it's actually higher than 0.4, even though in this case it was higher than 0.4. So we failed to reject the null hypothesis. There is not evidence that it is higher than 40%. What is higher? The proportion of customers who come back, portion of customers who come back with $10 coupon. I would probably write a lot more if I was actually doing this. I'd probably write just all the words that I'm saying, just to make sure I got everything right. But I feel like that's still good. So, B. Let me check that answer for part A. That was so long. Let me check that answer. Wow, they were quick about it. Wait, was I supposed to perform it? No, it says complete it. What? So they got the same value as me. Oh, there's 3 sections in A. Okay, got it. So, first, check the independence condition by referring to the random selection of 90 and indicating that the company is assumed to have at least 900 customers. Probably more than 900 customers. Lovely. Checks the sample size is large enough to support the assumption that the sampling distribution is approximately normal by verifying 90 times 0.4 and 90 times 1 minus 0.4 are greater than 10. Yes. Correctly reports the value of the Z statistic. That shouldn't actually be necessary. Wait, what? Section 1. Wait. States the correct equality for the null hypothesis for a proportion of equals 0.4 and the correct direction of the one-sided is greater than 0.4. Yes, I got that right. And I use the correct notation and everything. You'll love it. Appropriate test is a one-sample Z-test for... I said proportion instead of population proportion. That should be fine. We can look at that. Provide sufficient context for the parameter by including reference to the population proportion and sampling units of customers and the response variable. Wait, what? Let P represent the proportion. Oh, I never defined my P. I never defined my P. Let P represent the proportion of all customers of the pet supply company who would place an order within 30 days. Okay. I never defined that. That's all. Provides evidence... Identifies. So I didn't do number 2. Do they have any elements of the elements of component 2 do not have to be satisfied with the statement of the hypothesis. They may be satisfied by work presented anywhere in the response, most likely by the statement of the conclusion. Ah. Okay. So I did do that, just not there. Got it. Got it. I never use those symbols. I should be good. I think I should. I really think I'm good on that. Checks for independence condition. Okay. I shouldn't need to calculate the z-score. I did. I never reported it. But I shouldn't have to calculate the z-score. So what is that? Component 3. Confidence interval approach. I did that too. Oh, except for they got 5.524. How do they get 0.524? When computing the test statistic using a p-hat of 0.42 in the numerator results in a test statistic equal to 0.39 with a p-value of 0.36. Wait, what? I also got a different p-value. Because they use 0.43. Oh, no, because that was their z-score of 0.43. How did they get a different p-value than me? Like, that's decently different enough. The mean is 0.4. The standard deviation. Should I have been more specific about that? It's the square root of 0.4 times 0.6 divided by 90. And the mean is 0.4. And I still want the left side. And I wanted 38 out of 90. Oh, wow. That changed a lot. Okay. So just with rounding issues. So I did everything right. It's just there were rounding differences. Wow. But I really think that's honestly fair. Yeah, with a p-value of 0.36. I just didn't calculate the z-score, but I shouldn't have to calculate the z-score. So then provides correct justification of the conclusion. Because the p-value is greater than 0.05, the null hypothesis should not be rejected. The results from this study do not provide consistent evidence of this manager's belief. That is, therefore, there is not convincing more than 40%. Yeah, I definitely said everything with that. So there were rounding errors, but I still got all the numbers right. The decimals just made a big difference. I didn't calculate the z-score, but I really don't think I needed to calculate the z-score. Oh, wow, and now there's errors. Based on your conclusion in part A, which of the two, type 1 or type, could have been made? So, yeah, I always forget that. I always remember 2 not true. But I don't even remember what that refers to. The null hypothesis not being true. Or was it type 1 just like the normal one? I mean, what's the normal one you expect? The one you expect is like... Well, I guess there's really not one you'd expect, is there? So I'm thinking 1 is when the null hypothesis is true. But you said it was not true. So the 1 is... So this is 2. Type 2. because we failed to reject and in a type 1 you reject. I'm pretty sure that's true. So type 2 because we failed to reject the null hypothesis, which means we should have rejected the null hypothesis. Is that correct? I need to Google this before I proceed. Oh, I think I totally messed it up. A type 1 error is a false positive where the null hypothesis is not true, but you say it is. In formal terms, if a null hypothesis is rejected, even when it is true, and the alternative hypothesis is accepted. So in a type 1 error, you reject the null hypothesis. Oh, that is what I said. In a type 1 error, in formal terms, if a null hypothesis is rejected, even when it is true, and the alternative hypothesis is accepted, this is known as a type 1 error. Type 2 error, if the null hypothesis is accepted when it is false. Oh, right. You're supposed to remember the boy who cried wolf story. That at the beginning, he's like, oh my gosh, there's a wolf, when there's not a wolf. So he's rejecting the null hypothesis. He's normally, like, the null is that there's no news. He's saying, oh my gosh, there is news, when there shouldn't be. That's a type 1 error. And then at the end, he's like, well, he doesn't say there's no wolf at the end, does he? Is it what the villagers think? Well, no, then at the end, there is a wolf. And he said there's not. How did not the big bad wolf, that's totally different. The boy who cried wolf, maybe it doesn't totally apply to this. The type 2 error, there is a wolf, but they think there's not. It is so based on the villagers. So at the beginning of the story, he tells everyone that in the beginning of the story, everyone thinks there's a wolf, but there's actually no wolf. Everyone thinks there's news, but there's actually no news. Everyone is rejecting the null hypothesis when the null hypothesis is true. But at the end of the story, everyone is accepting the null hypothesis or failing to reject the null hypothesis because they're like, oh yeah, there is no wolf, but there actually is a wolf. There actually is news. That's how you're supposed to remember this. So in this case, we're saying that there's no news, but maybe there is news. So in that case, it's a type 2 error. We're saying there's no wolf, but maybe there is a wolf. So it's a type 2 because we failed to reject the null hypothesis, and in a type 1, you reject the null hypothesis. So in this case, it is possible it does have an effect, but we don't see that it does. Okay, that was iffy, and I had to do some Googling. But notice that I got it right, and notice that it just confirmed my understanding of the issues. Okay, so let's look at this. Part B. Or did I do this? Oh, no, yeah. States that a type 2 error could have been done, provides a reasonable explanation and the consequence of the stated error, and uses sufficient context by including at minimum, those who would place an order or coupon or sales. Oh, wow, I totally didn't do that. That was bad. And again, because of it, I needed to just say, it is possible that giving the coupons, and then I would have got full credit. But because I said it, I definitely would not have gotten full credit. Shouldn't use it. Should refrain from using it if you can. All right. Number 5. We're definitely behind schedule now, but it's because of checking answers. So number 5. A research center conducted a national survey about teenage behavior. Teens were asked whether they had consumed a soft drink in the past week. The following table shows the counts for 3 independent random samples from 3 major cities: Baltimore, Detroit, San Diego. Love it. It's all pretty similar from first glance. Suppose one team is selected from each city's sample. A researcher claims that the likelihood of selecting a teen from Baltimore who consumed a soft drink in the past week is less than the likelihood of selecting a teen from either one of the cities who consumed a soft drink in the past week, because Baltimore has the least number of teens who consumed a soft drink. Well, no, that's not true. No, because the population was just lower. No. Oh yeah, look, San Diego is half. No. This does not take into account who you're choosing out of. The total populations. Baltimore has a lower total population. Yeah, I mean, that's why. Yeah, that's all I'm going to say. B, consider the values in the table. Construct a segmented bar chart of relative frequencies based on the table. Okay, so for each city. Got it. So we just got to estimate these percentages. We just got to say, like, go back to calculation and say we're going to look at 727 out of 904. So in Baltimore, 80%. Oh, wow, wait. I was looking at it the wrong way. In Baltimore, so it might be true, but they're still wrong. Did I need to calculate anything? No. So here, 80%. That's pretty right on, actually. So 80%. I guess it's just yes and no. Yes, no. The next one is 1, 2, 3, 2 out of 1, 6, 6, 3. That's about 75%. So their data is correct. Their conclusion is wrong. And then San Diego is 1482 out of 2280. So exactly 0.65 of no and yes. All right, that's really kind of it. Which city had the smallest proportion of teens who consumed a soft drink in the previous week? San Diego. Smallest proportion of teens. Yeah, I just did. It's 0.65. I had to do that to do the graph. Consider the inference procedure that is appropriate for investigating whether there's a difference among the 3 cities and the proportion of all teens. Oh, I don't really know that. Identify the appropriate inference procedure. So it's a chi-squared because there's multiple things. Chi-squared for independence. Is there still... Let's look at the formulas. So I really, really don't remember these. The chi-squared type of stuff. But I think the names of them will at least be on here. Well, yeah, the chi-squared statistic. It's really just are independent, not independent. Isn't that what the chi-squared is? Identify the hypothesis The null is that they are independent. The alternative is that they are not independent. I'm actually not sure about that, so don't let me steer you wrong. Make sure you stick around for the answers here. Oh, good. That's it. Okay, good. Let's check the answers. Okay. No, it's not correct, even though it is true. Identifies research is not correct. Provides explanations based on the proportions and relative frequencies should be compared as the sample sizes are unequal. The proportion of Baltimore teens who consumed is larger than the proportion for at least 2 of the cities. Oh, right. Well, I said the total population should be used. I think that's fair. Okay. Next. Okay, that's not going to help me. Next is this. That's exactly what I did. I labeled it on the chart. Constructs a segmented bar graph where the bars are correctly segmented. Includes clear labeling of the proportions of teens. I mean, yes and no. That's what they did in the thing. Identifies San Diego as the city. Reports the correct numerical who consumed for the city identified in that, which is 65. Yes. Labels and yes and no may satisfy component 2. Lovely. It does very specifically say that. Okay. This one, though. A chi-square test for homogeneity. Is that not the same thing? There is no difference. So here they're looking at, so we're looking at difference, not independence. Or satisfies components 2. So I didn't satisfy component 2, but I did say the chi-squared, so I'd get a P. Thank you. So I see no mention of the independence thing. Got it. So it's for homogeneity instead of independence. Isn't that like the same? Isn't that like the same thing? Chi-squared for independence or chi-squared for homogeneity? Or are those different things? There are 3 main types of squat tear tests: goodness of fit, independence, and homogeneity. What's the difference? The main difference is to remember between the two is that the test for independence looks for an association between 2 categorical variables within the same population. In several populations. But this is like one population, Americans, and we have multiple different, we have city that they live in and whether they drink soft drinks or not. Huh. Well, I guess I just got that wrong then. That's okay. So that should have been for. Well, I don't need to rewrite it. I'll just look at what we should have said up here. So we should have said for homogeneity. Since the data were collected from independent random samples from 3 different cities, and we're looking at if they're the same, then I really feel like it's okay. I really feel like they're both the same. And then we should have talked about there's no difference, or there is at least one difference in the proportion. At least one difference. That's weird. How can there be one? How can there be multiple differences? You're just looking at differences between numbers. Well, I guess between all the different cities. Yeah, I'm hard to agree. It's hard for me to agree that those are different. I need to look more into chi-squared to see what's the difference between independence and homogeneity. They seem very similar. Anyway, number 6. This is the toughie. How's the time? We should be at 1:05. We're 5 minutes over, but we're also checking answers. That's why. So 6. Attendance at games for a certain baseball team is being investigated by the new owner. The following box plots summarize the attendance measured as average number of attendees per game for 47 years of the team's existence. The box plot includes the 30 years of games played in the old stadium and 17 played in the new stadium. Oh, I've done this question before. Compare the distributions of average attendance between the old and the new stadiums. So what's the acronym we're supposed to use here? Why am I blanking on that? Center, spread. Oh, SOX. Right. SOX. So we go. Of course, a lot of them start with an S. So the spread. The spread is pretty similar, aren't they? So the spread in the old stadium was from about 11 and a half. Or the range is like 11 and a half to 22. Old range is roughly 11. New range is about 16 to 28. That's pretty similar. It's hard for me to even say totally. I'm going to say it's about 11. It's about 11. They're roughly equal. I'm going to give it that. Outliers? Well, you can't really show outliers. Center. Old stadium median is much lower. 16 is less than 25. Shape. Old stadium is symmetric. Old stadium is symmetric. New stadium is skewed lower. Well, what is that? The tail, yeah, the tail is lower. So it's skewed to the left because more of the data is higher. New stadium is skewed left. Okay, yeah. The following scatter plot shows average attendance versus year. Okay. Compare the trends in average attendance over time between the old and the new stadium. Wow, so now we got like dots for both of them. Okay. So we got direction. Old stadium is pretty constant. I'll just say that. Pretty constant. New stadium is positive / increasing. Outliers, neither really have any outliers. Form, I mean, they're linear. They're pretty linear. Well, the old stadium has like no association. New stadium, I'll use a wiggle word, is roughly linear. And then, so direction, outlier, form, strength. Old stadium has very low association. New stadium has a much stronger association. Okay, that should be good. Now we're getting into the spicy parts. Consider the following scatter plots. Number of games won versus average attendance. And then the next one, average of games won versus average attendance. Graph 1 shows the average attendance versus number of games won for each year. Oh, so this is taking away the time. This is just showing that it's more based on their winning seasons, and then when they got their new stadium, they just started winning more? That's kind of weird. I guess that's not that weird, actually. Graph 1 shows the average attendance versus games won for each year. Describe the relationship between the variables in graph 1. Hold on, I dropped my pencil. All right. Graph 1 shows the average attendance versus number of games won for each year. Describe the relationship between the variables. Yeah, so as games won per year goes up, the attendance goes up. Graph 2 shows the same information as Graph 1, but also indicates the old and the new stadium. Does Graph 2 suggest that the rate at which attendance changes as number of games won increases is different in the new stadium compared to the old stadium? Not really. No. Because both sets of dots follow the same trend. I could even say if you calculate the best fit line, if you calculate the best fit line for each set, they would be very similar. Not exactly the same, of course, because they never are, but they would be very similar. Consider the three variables: number of games won, year, and stadium. Based on the graphs, explain how one of those variables could be a confounding variable and the relationship between average attendance and the other variables. Other variables? Oh yeah, so year versus stadium. So that was the idea that when we looked at this first graph, we were like, oh yeah, the new stadium is killing it. As soon as we hit new stadium, we started going hard. But you can't even compare like the old years in the old stadium. So consider the three variables: number of games won, year, and stadium. Based on the graph, explain how one of those variables could be a confounding variable in the relationship between average attendance and the other variables. Okay. So we have to say, like, I mean, I'm going to go with number of games won is definitely a confounding variable. The way they're phrasing it seems like you could use all of them. Number of games won is a confounding variable. But explain how the effect it would have on it. Because it has the strongest effect on attendance. And with the new stadium, they started winning more. So you can't isolate the effects of the stadium / year. I think that's pretty much it, I think. Because stadium and year are the same thing, because they got a new stadium like when the year happened. All right. I like it. Let's move on. Whoa, that's it? That was a weak question 6. That was a weak question 6. I feel like it was all pretty straightforward. Unless I didn't say stuff they wanted to. It was a lot of work in comparing these distributions, I suppose. They used a lot of words, more than I did. Indicates that the median average per game attendance is greater in the new stadium. Yeah. Well, I said, yeah, same thing. Indicates that the variability in the average per game attendance is greater in the new stadium. I didn't say that. Oh, I said they're roughly the same. According to the IQRs. Well, I didn't say that. I said they're roughly the same based on the range. I said they're both roughly 11. I feel like the ranges are about the same too. Whoa. Does my math suck? Yeah. Wait. The range isn't 11. It's going... Oh my gosh. I calculated that range totally wrong. I'm such a bot. And I even saw that the IQRs were basically the same. I could have just said that I was using the IQRs. Oh my gosh. My math is awful. In reality, this was roughly 12. And the other one was like roughly 9. So the new is greater. That's really what I was going for. I should have said IQR. That's unfortunate. That's unfortunate. And then provide sufficient context by including the response variable. Oh, right. And then I always need context by including the response variable, average attendance, or the units of response variable, thousands of people. No, I didn't do that either. I gotta remember context. That's the secret extra C in socks. Context. Yes. Okay. Describe the direction of the trend and average as the new stadium is increasing. Describe the direction of the trend, the average in the old stadium is relatively constant. I did that. Provide sufficient context by including the two groups and the explanatory variable and the response. So again, I didn't do context. Man, that's another P. Wait, is this all here? This is in part C? Oh gosh. So here I had to do all the DOFs? Oh no, I had to do dots here too. I had to describe the direction as positive. I did that. I didn't say it was linear. I didn't say the strength. I did say the rates are about the same for the two stadiums. Provides an explanation that the line were drawn through the points of the old stadium. The slope would be roughly the same. Oh, wow. I actually did have to say that. Okay. Well, I had to specify the slope. I didn't specify the slope. Is that okay? Okay, so I didn't do very well on that one either. Well, I got two of them wrong, so I got a P. I didn't do two of them. I didn't say it was linear or that it was strong. Dang, if I just would have done one of those, I would have gotten everything. So the next... Oh, that was that. And then that's this. Say there's an association between attendance and one of the explanatory variables. What did they say? The number of games won could be a possible confounding variable. That is what I said. For assessing the potential effect of opening a new stadium on the average per game attendance, the box plots in Part A show that the average attendance per game has tended to be higher for games of the new stadium than the games of the old stadium, but the cause of that increase may actually be that the attendees were more excited about attending games for teams that were better at winning. The scatter plot in Part C showed the average game presents a strong positive correlation, and the teams tended to win more games with playing in the new stadium than the old stadium. Yeah, I mean, that's basically what I said. There's so much stuff here. States that there is an association between attendance and one of the explanatory variables. Yeah, number of game wins. And that was the strongest effect on attendance, that's association. States that there is an association between attendance and a different one of the explanatory variables. Well, I didn't say that. I said the new stadium they started winning more. Oh, I guess I did say that. Stated there's an association between the two explanatory variables. No, so I did say when there's a new stadium they started winning more. But I didn't do number 2. Explains the idea that the variable identified could be the cause of association. I did say that. So I needed to also say that has the strongest effect on attendance. That the new stadium also had. So I needed to say that in the new stadium there were more wins as well. Yeah, so we got the gist of all of those in reality, and I think I covered everything that was slightly wrong, and we even finished in the time interval. And I might have just picked up the stuff by just writing books on the real test too. But we definitely explained all the answers if we didn't write them all down the first time. And I hope that was helpful. You got 1 week till the real thing.